Well, hi guys, this is Mr. Marek, and this is our first video of AP Physics 2. Our first unit in AP Physics 2 is on fluids, and we're going to start by learning about fluids which are at rest, fluids that aren't moving. And so we're going to be all Hollywood with this. We're going to call this video Hydrostatics, namely we're going to focus on pressure. So let's kind of break that word down. Hydro is a fancy word meaning fluid. Typically, when we think of hydro, we think of water, like a hydro electric dam, but it could be any fluid that we're going to be studying. And of course, static means at rest. So hydrostatics means we're studying fluids at rest. And at the end of this, we want to understand the idea of pressure. Why do fluids exert pressure, and how do we characterize and measure that? First, we need to understand a few things. When we study fluids, we have to consider them to be a system. Remember, a system is a collection of objects where we can ignore the internal structure. So when I draw a beaker full of water, I don't care that the water molecules inside the beaker exerting forces on each other. All I care about is the fluid as a whole, as a system, which is really going to make things simpler. So keep that in mind. Everything we do in our fluids unit, we're going to be treating a fluid as a system, which is a collection of objects. In this unit, we're only going to be dealing with ideal fluids. An ideal fluid means three things. One, it's incompressible, meaning you can't squeeze it and change its volume. Another way to say that it's got a constant density. The second thing is that when these fluids start moving, they move with a streamline or laminar flow, which means all the fluid moves in the same direction. Obviously today we're just talking about fluids at rest, so that idea is not going to be too important. We have a while to understand that. And then the third thing that we have to understand about an ideal fluid is that there's no friction between the fluid and its container. And so water moving through a pipe moves without the pipe slowing it down, in other words. The term fluid can refer to both the liquid phase and the gas phase, but only liquids can be ideal fluids because only liquids can be incompressible. So we're going to use gases to demonstrate some things, and we're going to talk about gases as being fluids, but really we can only characterize and apply equations to liquids in this unit. We'll get into a deeper study of gases in our next unit on thermodynamics. The best way to characterize a fluid is by its density. When we do physics with fluids, both the mass and the volume are going to be important to us. And so the mass and the volume of a fluid are related by its density. So that makes density the most useful way to describe a fluid. You should know about density already. You should know from chemistry that density is mass over volume. In chemistry, you use density as a way to characterize things. Metals are typically denser, etc., etc. We need to have more of a conceptual understanding of density as well as a quantitative understanding of density. The symbol for density that we're going to use, the big boy symbol, is the Greek letter rho. So it's kind of like a italic-y looking P. It's called the Greek letter rho. Don't use a D for density because then you're going to get that confused with a D for depth, which is going to be important for fluids. The unit for density that we're going to be using, our unit for mass is a kilogram. The unit for volume is a cubic meter, and so the unit for density is a kilogram per meter cubed. In chemistry, you probably use grams per milliliter as your unit for density, but because we want to keep things in terms of meters and kilograms so that things can be in newtons and joules and those kind of units, we need to use kilograms per cubic meter as our unit for density. Now this is a ridiculously small unit. Imagine how big a cubic meter is. Take a meter stick and hold it one direction, and then move it perpendicular and move it perpendicular again. Trace out a three-dimensional box. There's a cubic meter on each, that is a meter on each side, and that would be a pretty big box. You can fit a couple of people inside a cubic meter. And so a kilogram per cubic meter is really, really small. So to write the equation, it would look like rho equals m over v. Density is mass over volume. When we're dealing with just ideal fluids, which are incompressible, the density of those things are constant. So if I say the density of a fluid is this, then that density doesn't change regardless of what happens to the fluid. The density of pure water in kilograms per cubic meter is 1,000. So again, if you remember from chemistry, the density of water was 1, but that was 1 gram per milliliter. In kilograms per cubic meters, the density of water is 1,000. It's important to pay attention to your units, especially if you're going back and forth between the different classes. So, a real simple example. Suppose we wanted to know the mass of 2 times 10 to the negative third cubic meters of water. Then that may look like a small number, but remember, a cubic meter is a very large unit. So that's a pretty reasonable amount of water. That would be like something you would put in a pitcher or something like that. So we know that density is mass over volume. And so rearranging that equation, solving it for m, we would get rho times volume equals mass. We know the density of water, 1,000 kilograms per cubic meter. We're given a volume of water, 2 times 10 to the negative third meters cubed. And so if we multiply those together, we'll get our mass. Notice that the meters cubed cancel out, making my final unit kilograms. And when you multiply those two numbers together, you would get 2. And so that volume of water would have a mass of 2 kilograms. Again, that's a reasonable amount of water like you would put in a pitcher or something like that. So it's a simple relationship between mass, volume, and density, but it's one that we're going to be using often. Remember in physics, mass shows up a lot in our calculations, but fluids are more easily measured by their volume. If I say go measure out an amount of water, you're going to get a measuring cup or a graduated cylinder, not a scale. And so we need to be able to convert back and forth between volumes and mass throughout this unit. So now that we understand the term density, we can understand the term pressure. The definition of pressure is simply force divided by area. Pressure we symbolize with a capital P. Area we symbolize with a capital A. And of course, force we know is a capital F. And so our real simple relationship looks like this. P equals F over A. The unit for pressure, remember force is in newtons. An area would be a meter squared. That would be the SI unit for area. And that unit is typically referred to as a Pascal, named after a cat by the name of Blaise Pascal. A Pascal is symbolized with a capital P lowercase a. So hopefully we don't get that confused with the symbol P for pressure. Again, the Pascal is a very small unit. A meter squared is a large area. That's like if you took 4 desks and put them together, the area of the desk would be about a meter squared. A newton is a pretty small unit for force. Remember, a newton would be about the weight of 10 paper clips. And so that's a pretty small unit for pressure. Some other units of pressure you may be familiar with. Pounds per square inch, which is often referred to as PSI. If you watch the weather, they may give pressures in millimeters of mercury, abbreviated mmHg. Hg is the atomic symbol for mercury. And another common unit for pressure is the atmosphere, which is abbreviated ATM. The only one out of that list that we're going to need to know is probably the atmosphere. And an atmosphere is defined as the pressure due to the air, aka the atmosphere, that is surrounding us, and it's kind of an average value at sea level. So obviously the air pressure changes depending on where you are, but we kind of take an average value of the air pressure at sea level, and that's what an atmosphere is defined to be. A more precise definition in atmosphere is 1 times 10 to the 5th newtons per meter squared, or 1 times 10 to the 5th pascals. That's approximately 14 pounds per square inch. So if you're standing at sea level, then the air is pushing on you with a force of 10,000 newtons for every square meter of your body. So if I were to, take your skin off and stretch it out and measure it, depending on how big you are, your skin area may be close to a meter squared rather. And if that was the case, then the air pressure would exert exactly 10,000 newtons of force on you. Something that's probably more easy for you to see, if you look at that 14 pounds per square inch, that means that each square inch of your body has 14 pounds of pressure pushing down on it. 14 pounds of force pushing down on it. So think about how many square inches of surface area your body has, and kind of add those up, and that would give you the idea of the weight of the air that's pushing down on you. It's actually pretty large. We just don't notice it because we're used to it. Now the reason that fluids exert pressure, before we get to that, pressure exerted by a fluid is always perpendicular to the surface that it's exerting on. And remember, when something's perpendicular to a surface, we say that the direction is normal. And so pressure exerted by a fluid is normal to the surface. So if we kind of draw a flask of water, it may look like that. The pressure on the bottom is downward. That's perpendicular to the bottom. The pressure on the neck of the flask right there would be like to the right. That's normal to that surface. And on the slanty part of the flask, the pressure will be kind of up and to the right, like that. So the pressure is always normal to the surface that it exerts on. Now that could even be the case if the surface is imaginary. Now you would say, well, why would we have an imaginary surface? Well, when we derive the buoyancy relationship in our next lesson, we're going to, just take a chunk of water to study, and that's kind of how we're going to approach it. So it's actually something we're going to do quite often. So suppose that we have a large sample of water, and we just take like a small chunk out of it. It's like that triangle represents a piece of the water that we want to study. Well, the pressure on that piece of water is always perpendicular to the surface relative to the other water surrounding it. So the pressure on that triangle chunk of water that we randomly picked out of there would look something like that. Now the reasons that fluids exert pressure is because they have weight. Remember, weight is simply another term for the force of gravity. And so if we take a somewhat simpler shaped beaker of water like this, and the area of the bottom of the beaker was A, and we filled it up to a depth H, then the pressure on the bottom of that beaker is due to the weight of all the water pushing down on it. And so in our equation, pressure equals force over area, we're just going to say that that's the force of gravity over the area. So all that water pushes the bottom of the beaker because of its weight. That's what causes the pressure. Now remember that the force of gravity is equal to m times little g being the value of the gravitational field, which you should remember has a value of 9.8 newtons per kilogram. And so what we need to do is we need to figure out the mass of that water in terms of its volume. Volumes are things that we can measure about fluids, and as it turns out in this case, it's actually going to make things simpler. So I can figure out the volume of a beaker of water. It's simply length times width times height, or area times height. And so the volume of this beaker of water is A times H. Also remember that density is mass over volume, and so the mass of the water would be its density times its volume. And so I can combine those two ideas together, and say that the force of gravity is the density times the volume times g, and get rid of the m. And then, if I start substituting that into the pressure equation, I get pressure is equal to the mass times g over a. Instead of mass, we've got density times volume. And then if we realize that the volume is the area times the height, and we substitute that in for the volume, notice that the a's cancel out, and we get an equation that looks like that. Notice in that equation that the area of the beaker canceled out. The pressure is only affected by the depth of the liquid, or the fluid in general, not the amount. And so if you have a tall, thin beaker of water versus a short, wide beaker of water, the pressure is going to be greater in the tall beaker of water because the depth is greater. So that's the only thing that affects the pressures, how deep you go. If you've ever been swimming in a swimming pool and you've kind of dived down deep in the swimming pool, you've probably felt that. The deeper you go in the swimming pool, the greater the pressure is on your ears. If you've ever been in the ocean's got a bigger amount of water, but there's no greater pressure at a given depth in the ocean because it only depends on the height, not the amount of water. Now, when you use this equation, the equation P equals rho h times g, what this is telling us is the pressure caused just by the fluid, which we're going to call the gauge pressure. Remember that the air is still exerting pressure on everything around it, and so the question might be, how do we take that into account? And so if we want to know what the total pressure is on an object at the bottom of this beaker, we would call that the absolute pressure, and we would simply add the gauge pressure, which is what the equation gives us, to 1 atmosphere, or 1 times 10 to the 5th pascals of pressure. And so the reason that that equation, the rho hg equation, that quantity is called the gauge pressure is because that's what a pressure gauge actually measures. So if you've ever used a tire gauge, for example, and if you look at it when it's not connected to your tires, it's going to read 0. And the reason is that it was zeroed while it was actually in the air surrounding it. And so that doesn't take into account the fact that the air is exerting 1 times 10 to the 5th pascals of pressure. And so if we want to include that, we simply add it in after we use our pressure gauge to measure the pressure, or use the P equals rho hg equation to calculate the pressure. If you're just asked what is the pressure on something, well, then that's just asking you for the gauge pressure. They want the absolute pressure, they'll say, what is the absolute pressure? So here's a simple example. What is the gauge pressure at the bottom of a swimming pool? And we're going to have the dimensions of the swimming pool, 6 meters by 4 meters by 3 meters deep. So real quick, simple drawing. That's what my swimming pool might look like. We know that we can find gauge pressure using the equation rho GH. The H is 3 meters. The 6 meters and the 4 meter don't affect the pressure at the bottom. I'm going to assume the pool is filled with water, which is probably a pretty safe assumption. So I'm going to use a density of 1,000. G, I'm going to use 10, make my math a little bit simpler. And then our height is 3 meters. And so the gauge pressure at the bottom of this pool is 30,000. Now if we kind of take a second to look at the units, I'm just going to kind of combine the units like that real quick. I've got kilogram, I've got a meter per second squared, I got another meter, and then on bottom I've got meters cubed. And then the reason that I wrote it that way, remember that a kilogram times a meter per second squared is a Newton. And then once you remember that, hopefully you can see that other meter over a meter cubed would give you a meter squared on bottom. You could also write in scientific notation, and you can also write the unit as being a Pascal. Either way doesn't matter. You can write Pascal, you can write Newton per square meter. You just need to know that those two things are the same. In case a problem gives you pascals, you need to realize it's the same as a Newton per meter squared. If we wanted to know what is the absolute pressure at the bottom, well, all we have to do there is add in the pressure due to the atmosphere. The pressure due to the atmosphere is 1 times 10 to the 5th pascals. And so you add those together, you get 4 times 10 to the 5th pascals. So that's all you got to do to go from gauge pressure to absolute pressure. Okay, so that's the end of this video. But before you call yourself done, go back real quick and just review all these different units that we have to keep track of. Remember, units are very important. You need to include them in your work, but more importantly, you need to understand and identify from a situation what a quantity is representing. So if you see Newton per meter squared behind a number, you need to associate that with a pressure right away, even if it doesn't say pressure. Just take a minute and go back and review all those units real quick. Make sure you know what they are. And then we'll move on to the next video. Our next video will be on buoyancy, and we're going to learn what makes us float. Till next time, ta-ta.